All right, hello and welcome to a quick stream on or video on exploiting basic 64-bit buffer overflow vulnerabilities. As you can see, I don't have fancy graphics or anything yet. Hopefully, as I do lots more of these videos, I'll be able to ramp up on the special effects. But we just care about the content here, and I was surprised actually that some people requested this particular topic area, because when I do a search on YouTube, there are a ton of videos on this specific type of vulnerability. This type of vulnerability has been out there for decades now. I honestly thought that you wouldn't be able to exploit it anymore by this point in time, but here we are. We can still do it. Now, there are some good mitigations that have come or are coming out, such as shadow stacks and control flow enforcement technology, but these are not enabled by default typically. Like, for example, Windows Defender Exploit Guard on Windows 10 and Windows 11 does not turn that control on by default. You actually have to go into Exploit Guard or into the registry and turn that on. And most processors, at least at the time of this recording, don't support it yet. I think like Intel Tiger Lake CPUs do and a couple of others, but Microsoft certainly isn't going to turn that on by default until more and more processors are supporting that mitigation. Now, there are tons of other vulnerability mitigations, exploit mitigations that do protect against this classic old buffer overflow attack technique or vulnerability, such as data execution prevention, data or ASLR, so address space layout randomization, stack canaries, so on and so forth. There's a bunch of them, and depending on the operating system, you may come across one, two, or many of them. So what I want to look at, though, is just a basic vulnerability on a 64-bit POC, proof of concept program, that just allows me to explain what we're looking at a very basic level. And as I do more and more of these videos, even though, again, I wasn't planning on doing something at this level, I will make things more complicated. We'll add on mitigations, we'll add on protections, we'll look at ways to get around things. I am doing a stream on Fridays for the most part, and that's going to kind of be all over the place with different topics. But I'm also going to be doing recorded videos that I'll just upload like I'm doing right now on various topics, ranging from basic stuff like this and ramping all the way up into much more technical things. One of the things I'll point out here as well is that there's, of course, differences between Linux and Windows and Mac, and depending on the mitigations that are running and what's supported and what's not supported. But there's a lot of details that oftentimes aren't explained very well, and I wanna try and address those as well. So I may do some of these presentations where I address specific things that I consider to be like the glue between the concepts that helps it all make sense and ties it together. But as I've mentioned a couple of times now, since this has been done so many times, I'm hoping that what you get out of this recording is that I'm explaining it in a way that's hopefully answering some questions that maybe some of the other videos don't answer. So with that being said, let's just get started. I'm going to jump over to a Linux system here, and I'm using VMs that we actually use in the SANS courses for SEC 660 and SEC 760, which are advanced pen testing or exploit development courses. So I'm on an Ubuntu VM, and let's wait for this thing to open. Inside my directory here, I've got this little program called x64vuln. So if I run it, it just says enter a string of characters to get the length, and it gives me back the length. So to check for vulnerabilities, a basic buffer overflow vulnerability and things like command line arguments or input that's being requested, we typically just cram in a bunch of A's. And the reason that we use A is a capital A is the hexadecimal value 41. And we can see that by going into man ASCII. If we scroll down and look at A, it's the hexadecimal value 41 represents that. And what happens is if it's 64-bit and we cram 8 A's to the point where we're overwriting a return pointer or some other useful pointer that's being accessed, it should result in the values 41, 41, 41, 41, 41, 41, 41, 41 showing up in a register, because that's all those ASCII A's. And that is important because that memory location, that memory address of nothing but 4 ones, actually falls into an area we call the wilderness, which is basically unmapped memory that resides somewhere out there, typically like between the heap and the stack for the various threads and such. So since if you're talking about 32-bit, you've got a very small amount of memory, relatively speaking. You've got 2 gigs for the kernel, 2 gigs for user land on Windows. You've got 1 gig to the kernel, 3 gigs to user land on Linux, 32-bit by default in most cases. You can turn on physical address extensions or you can do other things, but let's not go there. With 64-bit, we actually get into like 7 or 8 terabytes per user land process, and then also for the kernel. So you've got a lot more memory that you're not using. It's just virtual memory that you're able to access. That's something I'll explain in another video, is how that works. Because if we've got 10 processes running and each of those processes is getting access to 7 or 8 terabytes of memory, we certainly don't have that much RAM on our system. So what's actually happening is you have access to that entire virtual address range, but you're only mapping and committing to a very small portion of that, which then has something called a page directory that maps over into the physical memory address that you're taking up. So even though you've got access to a ton of virtual memory, you're only using a very small subset of it. And when you think of controls like address-based layout randomization, that's what makes things challenging for attackers, because if we've got access to so much virtual memory space and we don't know where within that massive virtual memory range that a process is going to be mapped or a heap is going to be mapped, it's going to be difficult for us being the attacker to try and guess where things are located. So randomization is all about taking away that benefit that attackers have if you're not randomizing, which is the dependency on static addressing. So again, in another video, I'll explain kind of how virtual memory works, and we'll go through some of that. But in this case, we see that we're going to use A's. So let's get out of here, and I'm just going to send in a bunch of A's. So I'm going to use Python to do that, since this is command line. Well, it's not command line arguments. This is, we're running the program and it's prompting us for input. So I'm going to say Python -c print, and then we'll just do A times 1,000, because why not? We'll close that out. And we're going to pipe that as input to the program, x64 vuln. When we run it, you see we get the length of your input is 9.3, which is certainly wrong, but hey, we're crashing the program, so who cares? And it says segmentation fault. Now, just because you get a segmentation fault doesn't mean it's a Stack Overflow. This could happen when you have a read access violation or a write access violation, which means that you're going to a memory address that is not mapped. Again, it's either not mapped or the permissions are such where you don't have the right to actually view what's there or write to what's there. So don't assume that it's a Stack Overflow when you do this. It could be something on the heap. There's lots of things. It's a very generic message is what we're getting here. So we want to learn more. We can approach this many different ways. We can go straight into disassembly. We can go and look at it in a tool like IDA Pro or Ghidra. We can look at a decompiler and look at the pseudocode. Lots of different approaches we can take. So I'm just going to do a basic approach now. We're going to use GDB, the GNU debugger, to load up the program. So here we'll say GDB and then x64 vuln. Now when I load this, notice that it says GDB-PETA or PETA. That's the Python Exploit Development Assistant. It was written by Long Lee, and it's an extension to GDB that basically brings in a bunch of tools that we might want to run from an exploit development perspective inside the debugging session. If you've ever done anything on a Windows, from a Windows perspective, with regard to exploit development, you may have used Mona.py from Peter Van Ickhout or Corland Coder, which is a plugin to WinDebug or WinBGG or Immunity Debugger. Those two tools support that. And it is similar where it gives you the ability to run certain commands or tools or view things in a different way. You'll see some examples as we go through here. PETA actually also dumps out the context for us. So each time we pause or break, it will dump out things like the disassembly around where we're currently at. It'll dump things like where the stack pointer's pointing, the registers, and maybe some additional data that you'll see here very, very shortly. It doesn't come by default with GDB. You have to download it and run it, but this is one example of a tool. There's another one called Jeff, G-E-F, which is fantastic as well. There's also Pwn tools and lots of different things we can use, but I'm going to stick with Peter right now. And I'm simply going to run a very basic command called info functions. Very common command you would run first. What it's doing is listing out all the different functions that this program relies on. Now notice that some of them say @PLT, that's procedure linkage table. That's telling us that this program is dynamically compiled. It has dynamic dependencies, meaning that it's going to have to load libraries on your system. If you're to run my program on your system, it has a dependency on libraries that are likely on your system, and it needs to load them into the process. And then it needs to go through a thing called linking, where it actually locates the address of the functions that it has dependencies on. And it writes the results, it writes those addresses into something called the global offset table. What we're viewing here is the procedure linkage table, but it writes the answers or the addresses of those desired functions into something called the global offset table. Now that gives me another opportunity to mention an additional control that you may come across, which is called RELRO, R-E-L-R-O, relocation read only. What that is a control that does all the linking right at startup of the process, and then it hardens the global offset table by turning off the write permission, because there's well-known write what where attacks that allow you to modify pointers in the global offset table, where if you can do that, then anytime one of those functions gets called where you've overwritten its GOT entry, you get control. In this case, RELRO is not on, but it doesn't matter. We're not messing with that anyway. So we see some functions have @PLT. Those are the dynamic dependency functions that I mentioned already. And then other functions don't have that afterwards, like overflow or ASM or main. These are internal functions that are statically compiled as part of the code base. Now, going back to the procedure linkage table and dynamic linking thing, you typically don't statically compile a program, because that does a couple of things that you don't want typically. It makes the program unnecessarily large because you're compiling in those libraries, so it's a much larger program. The other problem with it is if there's a vulnerability that's discovered in one of those libraries or changes to those libraries, you now don't have the latest version or fixed version being loaded into the process when it's running. It's traveling around with a vulnerable copy of the library. So that's problematic as well. But down here at the bottom, we see that there's some internal functions that are part of the program itself that are statically compiled in. Now, we have the benefit here of actually seeing the functions listed on the screen. In most cases, or at least many cases, the developer of the program is going to strip the binary or strip the program. By stripping it, what that does is it removes the symbol names or the names of the functions that you see here, because the process doesn't need it to run. It works just fine with that. The only thing that you can't strip if it's got dynamic dependencies are those functions that are going through that whole PLT, GOT linking process. But the internal symbols or function names we can strip. But here we have the benefit of seeing them. And what I probably want to do is disassemble the main function. Disassembling is when we take the opcodes or the machine code and we actually disassemble it back to its mnemonic representation. I'll show you that real quickly. We're going to say disassemble, and then main was the name of one of those functions in a C program. And it's a very, very small main function that you see here. So see how it says on the right, push RBP is the very top instruction. That's actually the disassembled instruction. If I want to see the opcodes as well, we can say disassemble/R main. And then what you see here is the opcode. And then next to it on the right is the actual mnemonic or disassembled instruction for that opcode. Most people can't sit there and just write hexadecimal opcodes to write programs. Maybe a few can, but not many. So disassembly is a much better way of looking at things because we see the names, the instructions themselves. So notice that in the middle here, it says +0, then +1. Well, the reason it says +1 is because, as you can see with the 1 byte opcode, that's just a 1 byte instruction. But notice that down below that, it goes from +1 to +4. That's because the second instruction or line is actually 3 bytes. So the opcodes, 3 bytes of opcodes and operands, which is why you get that offset. So that number in the middle is simply the offset from the base address of the function. And then over on the far left, this is the virtual memory address. So we're looking at one single function within the code segment called the main function. Now, whenever you see this push RBP and then move RBP RSP thing, that's called the procedure prologue. That's what's used to set up a stack frame. So automatically, when you compile a program, you select the calling convention, and that's going to generate the code needed to both set up a stack frame and then tear down the stack frame. Every function call gets a stack frame. It's a finite memory allocation that's just there for the duration of the function call. Function calls, you use functions so you don't have to repeat your code all over the place. When we call a function, it does something for us, and then it returns back maybe something that we're expecting back from it, like a pointer to a memory allocation, or maybe just a status code, or maybe nothing. Something called the accumulator register is typically what's responsible for returning something back from a called function. But either way, the code to tear down that stack frame, that small memory allocation that's associated with each function, is dynamically handled, which is much different from the heap. The heap is much more complex. So we'll talk more about the heap in another one of these sessions, but for now we're looking at the stack. And I'm going to try and draw some pictures here as well, because I think they're helpful. I'm going to be using a drawing tablet, which I'm not the best artist in the world, but it's much better than not having something to visually look at. Now, one of the nice things is that the PETA, the plugin, is going to show us some really useful context information that we need. And you'll see what I mean when we get to that point. So right now, though, let's go ahead and look at this function called Overflow, because that sounds useful, right? It sounds like it's part of this POC that has a vulnerability in it. It's intentionally named that. So we get to this memory address here on the left. So this is an important thing to note. I'm highlighting on the screen the address inside the main function where there's a call to the function overflow. Now, typically when we call a function, we want control returned back to us. Once that function's done executing whatever it's supposed to do, we want it to return control back to us. So in order to do that, what we do is use something called a return pointer. So look at the address that I'm highlighting now. That is the address below the call to the overflow function. That is the address that we want to return to after the overflow function is done executing. At least typically that's what's supposed to happen. So in order for us to keep track of this, this return pointer actually gets pushed onto memory on that stack frame that I was describing, which I'm going to draw out here very soon. And that return pointer is how we're going to return control to our caller function, which in this case is the main function here. So let me start drawing a quick picture. I'm going to use my Windows VM over here to do that. I've got the paint tool ready to go, and I've got my drawing pen. So I'm going to draw a little stack here. So let's pretend that this is the area of memory known as the stack. Now, the stack typically grows from higher memory towards lower memory. So I'll put high mem, and then up here at the top, we'll put low mem. So it works in reverse of how you would expect it to work. And I'll put a little arrow just to make sure that that's clear. And then I'm going to draw a little stack frame here. And we'll say that this is the main function stack frame. So I'll just put main. Now, if we go back and look at the disassembly of the main function, you can see that at the very top, there's this push RBP and then move RSP RBP. Now, this is something called Intel disassembly syntax or assembly syntax. There's Intel and AT&T. GDB defaults to AT&T syntax, but since the PETA plugin is installed, it defaults to Intel syntax. And I don't want to go into too much detail here. Most people use Intel syntax, I will say that. And how you would read this instruction, for example, is, let me highlight it, is move into RBP RSP. Basically, it's a copy operation. We're taking the contents of the RSP register, which is the 64-bit stack pointer register, and we're moving or copying its contents into the 64-bit base pointer register. So it's just a copy operation. Now, what that means, though, if we go back over to our Windows system here so I can draw things out, is that let's say the base pointer is pointing down here currently. So I'll put RBP. Let's say it's pointing right there on the stack. And then up here is RSP. When that instruction executes, which was this one here, I'll write it up. It was move into RBP RSP, and I'll increase the font of that so it's larger. So move into RBP RSP. What that's going to do is take this RBP register and move it up to point to whatever the stack pointer points to. That's all that function, or that, I'm sorry, that instruction is doing. So for now, though, let's leave this alone because I want to focus on the function that we're calling, which is the overflow function. And let's look at that one because it's more important right now. So let's do a disassemble overflow. So this is a little bit larger of a function, and we can see there's a call to put string, there's a call to read, there's a call to string length, a call to printf, and then we return. So only a few calls in here. At the very top, though, is that same set of instructions. That's the procedure prologue. And then down here on the bottom, these two lines, that's the procedure epilogue that tears down the stack frame and returns control to the caller. So what I'm going to do is set a breakpoint on this address, which is the first instruction inside the procedure prologue code for the overflow function. What this code is going to do is set up the stack frame for the overflow function. So the first thing that's going to happen is we push the RBP register onto the stack. Let's get back to that. Let me set a breakpoint first. So break, I'm going to put an asterisk because I'm going to say a function name plus its offset. If you want to break on just a function name, you don't have to put the asterisk there. But if you want to break on a function name plus an offset or a memory address, you need to use the asterisk on the front because it's a pointer. So I'm going to say overflow plus 0, which is the very first instruction. If you don't specify the plus 0 and you just use the function name, it will skip the prologue because it thinks you don't want to care, you don't care about it. But I actually want to see it. And in fact, you know what we should do? We should set a breakpoint on the call to the overflow function instead. So let's do that. I'm going to delete my breakpoint. And then I'm going to disassemble the main function again. And we're going to break on main plus 9. So break main plus 9. And we're going to say run. So I'm running the program. And it immediately hits the breakpoint because the program is very simple. It did the, you can see up here, some of the things that PETA shows us is the disassembly context, which is really nice. Right here on the far left, you've got where the instruction pointer is pointing at this moment in time, which is where it should be pointing because that's where we set up our breakpoint on the call to the overflow function. We also see printed out by default, this is the stack pointer and the contents of what's stored there at those addresses. If you go up higher, you can see the registers pointed out or printed out by default as well. So right now, we're on the call to the overflow function. And here's some of that basic stuff I want to point out that I was mentioning that I've seen some videos out there that don't go through this level of detail. And I think it's really important to understand. So far, we've set a breakpoint on the call to the overflow function and we've simply run the program. That's all we've done. So now we're at that breakpoint. You can see that we're paused right there. You can see that little equals greater than sign showing us where we're at, and we're about to call overflow. The important detail I was just mentioning is the call instruction does two things. It takes the return pointer address, which is the next address down right there. That's going to be the return pointer, because when the overflow function returns back control to the caller, which is main, that's where we want to go, right after the call instruction. So that address that you see highlighted is going to be pushed onto the stack and serve as the return pointer for the duration of the function call. The second thing the call instruction is going to do is redirect the flow of execution to the actual code for the overflow function. So let's go ahead and mark that address. So I'm going to copy that address because we're going to see it show up here pretty soon. So over here, I'm just going to make a note and put RP for return pointer and paste that in, because we should see that get pushed onto the stack here momentarily. We go back over here, and I'm going to say SI in the debugger. SI stands for step instruction, so step a single instruction. And that will take us one step into the very first line of code inside the overflow function. Now look at the stack pointer right now. So how do I know that's the stack pointer? Well, one, that's what's printed there. But if I say IRRSP, that stands for info register, and then you give it the register or multiple register names. And it's telling me the RSP register points to this address. And as you can see, that matches what's dumped out here. That's a nice thing about PETA. It automatically dumps what the stack pointer is pointing to and the contents of that location. Now, as I said, I'm going to say SI, which is step one instruction. What you're going to see is that the stack pointer is going to move up towards lower memory, and it's going to be pointing to the return pointer that got put onto the stack. So we know what that return pointer should be. It should be right there, what I'm highlighting, 400631. So let's do it. And here you can see the stack pointer now points 4 bytes lower in memory, and it points to 400631, which is the return pointer now. So if we go over here onto our drawing, let's put that onto the stack now. This got moved there, and the stack pointer automatically adjusted to point to that return pointer that we just pushed onto the stack. Now, one important thing to note is that the stack pointer will always point to the top of the current stack frame. So each thread gets its own stack. So its own area of memory for stack frames. Each thread gets that. So whatever thread context you're currently under, the stack pointer will point to the top of that thread stack. The stack pointer always points to the top of the stack unless somebody hijacks it. So that's the call instruction having executed. Now, if we go back over here to our Ubuntu system and look at the program, you can see that the instruction pointer now points to the very first line of code in the overflow function, which is the procedure prologue. That's that little bit of code inserted in by the compiler to set up a stack frame. The first thing it's going to do in this case is push RBP. Now I want to point out something else that's important. RBP, so the R stands for register. That means it's a 64-bit register. RBP, register base pointer, 64 bits. If it were 32 bits, it would say EBP for extended base pointer. If it just said BP, that would be a 16-bit base pointer as we move up in architectures. So the base pointer on 32-bit processes has a pretty specific purpose. It's always used as the base pointer, which points to a static position in a stack frame for the duration of a function call. It is used so that you can reference local variables by looking at offsets from it. And I'm going to show you that. Now that's a 32-bit thing. On 64-bit, it doesn't always need to be used in that manner, because on 64-bit architectures, on x86, x86 64, we have 16 general purpose registers, processor registers for each core, versus on 32-bit where we only have 8 general purpose registers per core. So we get these additional 8 registers called R8 through R15 on 64-bit. And that being the case, we have more space to do things like pass arguments to a function call. It's not considered the safest way to do things by pushing arguments to a function you're calling that it might need onto the stack, because the stack is writable. So an attacker could potentially overwrite those arguments on the stack and change some things. Versus if you pass the arguments via registers, it could be a bit safer. So we have more space because of those additional 8 general purpose registers. Now, in this case, though, this is a 64-bit process, but it is using the base pointer in that more traditional manner. Again, it's not always the case. Sometimes you'll see it that way. Sometimes you won't see it that way. How do you know if it is being used in that way? Well, right there at the top of the procedure prologue, you can see it's being pushed onto the stack, and then the stack pointer is being copied over into the base pointer. That's how you know. I'll show you another way soon in IDA Pro. So right now we're about to push the base pointer onto the stack. So I'm going to say info reg RBP. This is the address that is currently stored inside the 64-bit RBP register. And it's saying we're going to push that onto the stack. So I'm going to grab this address and we'll go back over to our Windows VM. What that means is we are going to take that and push it onto the stack. So let's let that happen real quick. So I'm going to say SI for single step. And as you can see, the stack pointer now points to that base pointer address that got pushed onto the stack, followed by the return pointer, which matches what I just drew up here. Now, when we do that, the stack pointer automatically adjusts. So when you push something onto the stack pointer automatically adjusts to point to it. That's another important note. There are 3 very powerful instructions that are associated only with the stack pointer. That's push, pop, and ret. Push takes whatever you told it to push onto the stack and adjusts the stack pointer to point to it. Pop takes whatever the stack pointer is pointing to on the stack, pops it off of the stack into a designated register, and then adjusts the stack pointer towards higher memory. The return instruction is super powerful because it takes the address pointed to, or whatever's stored at the position pointed to by the stack pointer register, it redirects the flow of execution. You will hear people inaccurately say, I overwrote EIP or I overwrote RIP. You can't overwrite RIP or EIP. These are processor registers that are physically integrated into the processor core. So short of opening things up and using some special tool to do that, you're not overwriting it. What you are overwriting is a return pointer in this case, potentially, so that when that return instruction executes, you're redirecting the flow of execution to that address, which is important. It's an important distinction. So we just witnessed this happen. The instruction that was executed was push RBP. And I'll put that up here because it should go right on top of that next instruction that's going to execute. So we just saw push RBP happen. Now, this is an important note because when we are using the base pointer in this manner, it becomes something known as SFP, which stands for saved frame pointer. The saved frame pointer is going to be used to restore the base pointer back to where it was pointing. Because look what we're about to do. We're about to execute this instruction, move into RBP RSP, which is going to take that base pointer away from where it currently points. So that save frame pointer, the reason we're storing it there on the stack is so that we can restore the base pointer when we get to the end of the function and do the procedure epilogue. So next instruction that's going to execute here, as we look, is what we just talked about, move into RBP RSP. that is effectively going to do this. We're going to take the base pointer away from where it's currently pointing and point it up to wherever the stack pointer is pointing. So let's let that happen. If you look right now, you can see that the stack pointer is pointing right here. So if we look at the registers, info, reg, RBP, RSP, see how they're pointing to different locations? When I say step one instruction, they're going to both be pointing to the same location. See that? Because what we just did is what we just wrote up in this diagram. We moved and copied the stack pointer address into the base pointer. Now the base pointer is going to point to this static position for the duration of this function call. And the reason we like that is because let's pretend that there was some argument at this location. Arg, I'll put arg1, I'll put arg2. Let's say that that was the case. At +8 from the base pointer position is the return pointer. At +16 decimal would be argument 1, and at +24, because this is 64-bit, right, would be argument 2. We know that we can always access those arguments that were passed by referencing the base pointer plus those offsets. That's one of the things that's nice about it. Let's get rid of those arguments. Okay, so now we've completed the procedure prologue and we've set up the stack frame. Now let's look at the next thing that's going to happen. Now we're going to get into the point where it's important and relevant to the vulnerability. So the next thing that's going to happen is subtract hex 60 from the stack pointer. This ends up being the buffer size. We are allocating buffer space right now. So if we say Python, actually I'll say shell Python -c print 0x60. We should have been able to do that in our head, of course. 96 is the buffer size. So what we're about to do, if we draw this out, is allocate a 96-byte buffer. Like that. And we are going to subtract that value from the stack pointer, which tells the stack pointer, point to the top of the stack frame. The base pointer will stay pointing at the save frame pointer for the duration of the function call, but because we just subtracted, because the stack grows from high memory towards low memory, we've allocated 96 bytes of buffer space. So if we want to overwrite that return pointer due to a vulnerability, we would write 96 bytes plus 8 bytes for the save frame pointer, which is 104, and then we get to the return pointer. So we'll get back to that in a moment. And there's another way we can find this out as well if we don't want to do it this way. So let's go back over to our VM here, and let's step one instruction. So now you can see that the stack pointer points 96 bytes away from where it previously pointed. Now, there's a problem that's about to occur. Let's go over to our Windows system, and I've loaded this program into IDA Pro. Now, you could use Ghidra or anything, but right here, we're in the main function, and you can see the main function calls the overflow function. So if we double click on overflow, here is the disassembly. Here's that call to read that's going to occur. Here's that buffer allocation of 96 bytes. So 60 hex, 96 decimal. Now, right up here, you can see the buffer size being listed at the very top, hex 60. Here's the problem right there. The size argument that's being given to the read function, which is where the vulnerability is, because the read function has a size argument, just like strncopy and memcopy and others, but it depends how that size is being determined or calculated. In this case, it's been statically improperly placed. But you'll notice even in major vulnerabilities on Windows or other operating systems, the size argument for memcopy is often dynamically constructed, or size of something else. And if that size of something else, or the way in which the size argument's being constructed, is influenceable by an attacker, An example would be the SIG-RED vulnerability against DNS a year or two ago. There was a problem there where the way in which the size argument was being determined for memcopy was a little bit different than how the memory allocation was occurring, and it resulted in a heap overflow. Now, that's not the case here, but I'm just explaining that a lot of times the size argument calculation is bad. And a lot of people assume, well, as long as we're not using stir copy or gets where there is no size argument, we should be safe, right? That is not true. It depends as to how the size argument is being created. In this case, it's statically set at 300 bytes, 300 decimal bytes, or 12C hex. So now we know that there's a small 96 byte buffer allocation, but a function called to read is allowing us to write up to 300 bytes, which is going to, if we look back over at this diagram, if we've only allocated 96 bytes and we're writing from the low memory towards the high memory, then we're going to overwrite that return pointer and everything else on the stack. And that's what's going to end up giving us control. We want to overwrite this return pointer with something we control. That's supposed to say controllable, just bad handwriting. Controllable, because we're going to be able to overwrite it, redirecting the flow of execution. And that's what our goal is. So we could do this via another technique, which is using a pattern. It's a little bit of a lazy way to do it, but it works. Hey, why not when we have the opportunity? What we can do is utilize, it's been ported in as part of PETA. We can say pattern create. And what it wants is the size of the pattern you want to create. So I'll say, okay, pattern create 300 bytes. And it gives us this pattern to use. So I'm going to grab the pattern without the apostrophes. And I'm going to place that into the buffer here. So I'm going to say run. And I'm use a special syntax so I can send it in as input. I'll say Python 3 minus C print. And I'm going to say the pattern in quotes. And then we close that out and run it. So we hit the breakpoint. I'm just going to say continue. Now it crashes. See how it says segmentation fault right there? SIG-SEG-V. Up here, you can see that the instruction pointer is pointing to the return instruction. We overwrote the return pointer, but the debugger said we're not actually going to go to the address, because if you look at the stack pointer, what it would return to is this crazy address there. So it knows it's an invalid memory address, and the debugger is not actually letting us move forward into actually trying to execute what's there. But if we give it a real address that's mapped, it'll go there. We will get control. But the important thing about this is we can take this piece of the pattern, the 8 bytes, and what it should do is tell us the pattern size. Let me see if this works as is. I'm going to say pattern offset and paste in that piece of the pattern. And it worked. It says pattern offset found at 104. Now, the reason it's saying 104 is because it's 96 bytes for the buffer plus 8 bytes for the save frame pointer. That's 104 bytes before you get to the return pointer. So it's simply looking to see which piece of the pattern is ending up in the register, and then it's giving us the offset. So that's another way we can do it pretty easily. Now, what we want to do, though, is overwrite that address with something meaningful. So if we want to test this to make sure everything looks good, I'm going to say run, and then less than parentheses, we'll say Python minus C print A times 104 plus, I'm just going to put in plus B times 8. So A is 4.1, B is 4.2. So B times 8 should overwrite the return pointer, and then I'll close that out. And we hit the breakpoint. Now, if I look at the stack, so if I say something like x/20gx, that means examine 20 giant quad words in hexadecimal. Giant is quad word. And then starting at the stack pointer, RSP, it's going to start dumping out what's on the stack. And if we go down far enough to the right offset, we will see the actual, what the return pointer should be. So I'll do 40, And instead of doing it this way to try to find it, remember, we can reference the base pointer due to the fact that the base pointer is static at +8 from the base pointer. We can see the return pointer. So I'll say x/gx $RBP +8, which should be where the return pointer is located. Now, right now, I'm probably on that call because remember I had that breakpoint on the call to overflow. So maybe things are off right now. Let's say continue. And now it's seg false. So you can see we're on that return again, and the stack pointer points to the B's. So it did actually work. But let me take a step back. I'm going to delete my breakpoint, and we're going to set a different breakpoint. And I'm going to break on the call to read. So that's offset 35. So break on overflow plus 35. And then we'll run that again. So now we hit the breakpoint, and you can see we're on the call to read. So right now, if I look at that offset from the base pointer, that's what the return pointer is supposed to be. I'm going to say next instruction to step over the read function. And now if I look at RBP +8, you can see I've overwritten it with the B's. And if we continue, we crash. So that's determining the buffer size via reversing, via the pattern tool, and then validating that we can do that. What we want to do instead to gain code execution now, though, is notice that the stack pointer points to where we're going to return. So we're going to return to whatever the stack pointer is pointing to if we put something valid there. What we like to do typically in this case, if code execution is allowed on the stack, we'd say jump to the address in the stack pointer and start executing code there. Or we could overwrite the return pointer with a ROP gadget and kick off a ROP chain. But this is a simple little program. Stack protection is not on with dep. So I'm going to demonstrate that real quick, and then we'll call it for now for this particular walkthrough video. So I'm going to say this command, jump call RSP. That's a special command with PETA that's saying look through memory for any opcodes or instructions that are a jump or a call to the stack pointer. And it's giving us some options here. Now, the read function allows us to write null bytes too, which is beautiful. Functions like stir copy don't let us do that. So I'm going to change my input here. Instead of B times 8, I'm going to put that address in little Indian format, reverse order, because memory is written in x86 and x64, and reverse order is how you normally think it would. So we need to put the memory address in backwards so it writes it in the right order. It's kind of funny. So I'm going to put in 1E and then 064000. That's 32 bits. We need 4 more bytes of zeros. So 00000000. The /x means hexadecimal, if you're wondering. And then we're good. And then after that, I'm going to put plus hex cc times 16. Hex cc is the opcode for int3, which is a software debug breakpoint. We're going to do that. Let's look at the base pointer currently. You can see we haven't overwritten it yet. I'm going to say next instruction. And now we've overwritten it, or have we? Or is it changed or not? Yeah, we've overwritten it now with the address of that jump RSP. So I'm going to set a breakpoint on the, oh, I actually didn't mean to do that. Break for disassemble overflow is what I meant to do. I'm going to set a breakpoint on the return instruction. So break pointer overflow plus 83. Continue. Now we hit the breakpoint on the return instruction. Before, when we let this continue, it crashed because we had an invalid memory address. Look what's there now. We overrode it with the address of a jump RSP. So when I say step instruction, we are at the jump RSP. It says, hey, you know what? You're about to jump to the stack where you're going to execute these int3 opcodes, which are our CCs. So boom, we have code execution now on the stack. And if we look at that on this drawing here, what we've done is we've filled up this buffer here with nothing but A's. So 41414141, like that. 96 of them. And then we even got down to this point and we overwrote this return pointer, the base pointer, I mean, also with 41414141, because there's 96 plus 8. Finally, we overwrote the return pointer right here with the address of, I'll put pointer to jump RSP. We overwrote the return pointer with an address of a jump RSP, and then below that, we put CC, 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 which is a int3 software breakpoint. So CCs is an int3 software breakpoint. So what happened is when the procedure epilogue in the overflow function went to return, the stack pointer was pointing down here because of the epilogue. And when it went to return, it returned to a jump RSP, which said, hey, instruction pointer, go to whatever the stack pointer is pointing after we do the ret, which is pointing to those CCs, and it executed it. So that's pretty much the gist of it. Hopefully that was helpful for you and you learned a couple things. If not, go ahead and post questions in the YouTube comments. I will be on there and answer. It might not be super fast, but I'll check it every couple of days and I will happily answer questions. Also, give me ideas for more webcasts or things that you want me to produce. It can be as basic as possible. When I get time to do it, I'm happy to do it. And also, I'll be working towards more advanced stuff as well. But thanks for watching and good luck hacking.